So how do we define a polygon? So a polygon is kind of our general word for a shape with straight sides, but we want to be formal and precise with that. So we define a polygon as follows. We say a polygon is a closed shape made of straight sides that intersect only at their endpoints. So let me show you a quick example of a polygon. We have the classic pentagon. Now, a non-example, something that's not a polygon, is something like this, where it intersects at, we kind of have a crossing right here. So we want a polygon to only intersect at endpoints. Now we classify polygons according to their number of sides. So since this is 5-sided, we call it a pentagon. You likely recognize this as our 6-sided polygon, a hexagon. This is a 7-sided polygon, which we call a heptagon. Our classic stop sign, which has 8 sides, which makes it an octagon. For some reason, we rarely talk about the 9-sided figure. We usually jump straight to 10, and we call that a decagon. And we'll jump to 12 from there to make a dodecagon. Now, these all look very nice. That's because these are all regular polygons. What do we mean by regular? They all have side lengths are all the same. And interior angles are all the same. Let's look at a non-regular polygon. This mess right here. How many sides does this have? Let's see, there are 1, 2, 3, 4, 5, 6, 7. This is still a heptagon. It's not a very nice looking one, but since there are 7 sides, it's a heptagon. Often with stuff above a quadrilateral, something with 5 or more sides, we only think about their regular forms, but I can really make anything and name it according to its number of straight sides. Now, before we talked about the sum of the interior angles for a triangle, which you may remember had an angle sum of 180 degrees. And then for a quadrilateral, it had 360, and you may remember because it was formed of 2 triangles. Can we use a similar idea to find the interior angles of these? If you want, it might be fun to pause the video and see what you can figure out on your own. I'm going to go through them now. Once again, I can make triangles or even quadrilaterals. Here I can see this has to be 360 plus 180 for my angle sums. So this one ends up being 540. And then here, I can think of it as two quadrilaterals, or I can, whoops, that's not what I wanted to do, or I can just break it into a bunch of triangles. Hey, I can get 4 triangles out of this. 4 180s is 720 degrees. On a heptagon, a 7-sided figure, I can get 5 triangles. So 5 times 180 is 900 degrees as its angle sum. Now, without counting triangles, can you predict how much is going to be in an octagon? Well, I had 5 triangles here, so this should have 6 triangles. And so 6 times 180 is going to be 1080 degrees. This one's going to be 8 triangles. And so that makes it 8 times 180, which is 1440 degrees. And then for a dodecagon, it should end up with 10 triangles. Let's go ahead and build those real quick. I'll get a triangle here, a triangle here. Now notice these triangles may be a little small, but no matter the size of a triangle, it has an angle sum of 180 degrees. And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. So that means its angle sum is 1800 degrees. Now, does that work even when the shape isn't regular? Well, let's make triangles again. Let's see, I can put a line here, a line here, and a line here, and I count the triangles. 1, 2, 3, 4, 5. And we said this was a heptagon previously, so this must still have an angle sum of 900 degrees. This brings us to a pattern. Notice the number of triangles. How does that relate to the number of sides? Hopefully you've noticed it. It's 2 less than the number of sides. So we get this formula that the angle sum is equal to n minus 2 times 180, where n is the number of sides and s is the angle sum, because of the pattern we noticed where the number of triangles is always 2 less than the number of sides.